Okay, so now what we're going to take a look at is looking at combined masses in tension. And this looks similar to the one where we had those three boxes where we treat the object as one object first, and then we break it apart. So let's say we have two objects that are connected together, the string, and let's say the mass of this box, we'll call this mass 1, is 50 kilograms. This mass, we'll say mass 2, is 75 kilograms. And let's say this is being pulled upwards with an acceleration as positive 3 meters per second squared. And we want to find out what is the tension force here, what is the tension force here. So just like we did before, we're actually going to treat these two objects as one object, the whole system. So when we do that, we have object 1 and object 2, mass 1 and mass 2, we can figure out what that upward tension force is. Counteracting that would be the force of gravity of those combined. And so when we set up the sum of the forces, because I'm in the y, positive tension force plus the negative force of gravity equals the total mass, which is 125, times acceleration, which in this case is 3 meters per second squared. And we can figure out what that tension force is. So it's negative, let's see, 125 times 9.8 equals 125 times 3. And 125 times 3 is 375. 125 times 9.8 is 1225. And we can bring that over. So the force of tension on that top one is 1600 newtons. And then what we can do is, now that we know what's going on with that's the tension force here. Now we want to find is the tension force here. And in this case, we're dealing with just this object. So sum of the force in the y equals m in the y. We have the positive tension force here, and force of gravity of this one plus the negative force of gravity equals just the 75 kilogram object times 3 meters per second squared. And when we work this one out, we have the 75 times 9.8, and then we can find the tension force, and over here the tension force is 960. So quite a bit less, but that's because the tension force here is only pulling up this one. This tension force is pulling up both of them. So now, with the same kind of idea here, we're going to have, let's say we have two objects that are connected by a rope. And let's say this is on a surface with no friction. And we want to find out what the tension force is here, what the tension force is here. And let's say the mass of this one is 10 kilograms. Let's say the mass of this one is 17 kilograms. So just like we did before, we're going to make them both together. And let's say the acceleration is positive 2 meters per second squared as it goes to the right. So what I want you to do is see if you can figure out what this tension force is and what this tension force is, and based on that same method where we combine them together, treat them together, and then break them apart. And so yeah, why don't you go ahead and try that, and then you can resume the video when you're ready. Okay, so for the first part, to combine those together, we have both masses, and we can determine the force of tension, which in this case, having those two masses together, the tension force would be 54. And then for this one, just the 10 kilogram mass, we have the acceleration, we have the mass, and so the tension force felt there would only be 20 newtons. Okay, so now we're ready to introduce the inclined plane, and the inclined plane is an important thing to be able to understand and look at in terms of forces. So as we begin this, what we're going to do is take a look at a sample, and you're going to want a pretty big area for this. It's good to draw this out in a large area. Let's say we have an incline, and we have an object that's resting on the incline. And let's say it's frictionless, so this is naturally going to fall down the incline like this as it goes. And what we have here, we'll say that the angle down here is 30 degrees for the incline, and we have the mass up here, which we don't need yet. We're just going to look at the forces involved first. So the first thing that we're going to do is draw the forces. So we know we have the force of gravity acting straight down the center of the Earth, so we can draw that one. And we also have the normal force, which is acting perpendicular to the surface. And that's actually it. Those are the only two forces. So after we draw the forces, we want to draw the coordinate axis. And this is where it's kind of strange. We actually draw the x-axis parallel to the plane. So this would be the positive x, this would be the negative x. And then perpendicular to that, right here, this would be the y-axis. So negative y, positive y-axis. And the reason we do that is because the motion of this object is along the incline, and so we can use the coordinate axis like we want to there. As we continue this, what we're going to do is we're actually going to break down the force of gravity into two parts. We have the force of gravity here in the y, so FGY, and then we have the force of gravity in the x, FGX. And this angle here is actually the same as this angle. It's an alternate interior angle. So those angles are matching. So what we're going to do is, as we try to figure out what's going on, we're going to want to see, okay, what's the normal force? And then what is the acceleration of this object in the x direction as this object would fall down the incline? So as we set up the sum of the forces in the x equals ma in the x, the only force in the x we have is FGX. If you notice, this is perpendicular or parallel to the x-axis, so we have the positive FGX acting in the positive x here equals MAX. And then in the y direction, so the force of the y equals MA in the y, we have the positive normal force, which is up here, plus the negative force of gravity in the y, which is right here, equals MA in the x, or MA in the y rather. And as this goes down the incline, because it stays on the x-axis, it's not even moving in the y-axis, so the acceleration, the change in velocity is zero, it stays zero, so that's zero. So it turns out the force of gravity in the y is equal to the normal force. And we can determine that. We know the mass here is 125. And that's what we can find force of gravity, which is mg. And so we can determine both these values, FGY, FGX, based on the triangle here. This is 30 degrees, this is the adjacent side, this is the opposite side, this is the hypotenuse. So why don't you pause the clip and see if you can solve the rest from there. Go ahead and determine the normal force here, and go ahead and determine what the acceleration is of this object as it goes down. And then when you're ready, you can hit play. Okay, so the force of gravity in the y here is the adjacent side, and we can use the cosine. Cosine is adjacent over the hypotenuse, so cosine of 30 equals the adjacent side, which is FGY, over the hypotenuse, which is mg, which is 125 times 9.8, because that's the mass. And when we do that, we get 1060, 1060.88, and so that is the normal force. And then if we use sine, we can find the opposite side, and that gives us the value of 612.5 newtons, and we have the mass, so the acceleration in the x would be 4.9 meters per second squared, meaning that this is going to accelerate down at that rate. Okay, so now you're going to get a chance to practice drawing the incline and solving for the normal force and the force, or the acceleration in x. So first draw the incline, and then set up the sum of forces like we did, and yeah, and then you can see if you got it. So go ahead and hit pause, and then when you're ready, you can see how you did. Okay, so let's make sure your free body diagram's okay. We have our coordinate axis set up left to right here. We have the normal force going up, force gravity straight down the center of the earth, and then we have the force gravity in the y, force gravity in the x. The forces in the x and y, so the force gravity in the y is 405.9, the force gravity in x is 172.3. And for the forces in the y, you should have the positive normal force plus the negative force gravity in the y equals 0. There's no acceleration in the y, and so the normal force should come out as 405.9. And then in the x direction, we have the force gravity in x. We've got the mass, and then we can find the acceleration in the x, 3.83 meters per second squared. Okay, so on this one, we're going to combine the incline problem with motion. And so we have a 1 kilogram block that's sitting on the incline, and it's starting from rest, and it's on frictionless 20 meter ramp, and the angle is 15 degrees. So the first thing we want you to do, go ahead and draw the free body diagram of the object, and then you can solve for the acceleration in the x, and then once you solve for the acceleration in the x, we'll continue from there. We'll see if you can get that first. So go ahead and pause the clip, and then when you're ready, you can start. Okay, so we should have normal force, force gravity, the coordinate axis set, force gravity in x and y set up, so the normal force counteracting force gravity, and the sine of 15 would be the force gravity in x. And in this case, if you left it in variable form, and this I'll have you guys actually, you should ended up getting 2.54 meters per second as the acceleration. But what I want you to do is on your sheet of paper, go ahead and write this method as well. If you leave it in variable form, this is the FGX, that is mg, which is the hypotenuse, times sine of 15 using the trig. If you place that in there, you can cancel mass from both sides. And when you do that, it's actually, and this is really important, when you divide mass from both sides, you can see how the acceleration down the ramp is actually independent of the mass. And so no matter what kind of mass that we would have, the acceleration would be the same. So you should get 2.54. Now that you have that, we can look at the motion. The initial velocity is 0 meters per second. The acceleration is 2.54 meters per second squared. And it's a 20 meter long ramp, so delta x, 20 meter long. And we have the acceleration, the initial velocity, delta x. So we want to figure out how much time it will take for it to go down. So if you go to the one-dimensional motion kinematic equations, you can find what that is, and then go ahead and determine time. So go ahead and pause the clock and see if you can determine time. Okay, so you should have got 3.97 seconds is the amount of time that would take for the object to go down the ramp using one of the constant acceleration equations. Okay, for this one, to determine the angle of the ramp, we're going to use that same method we just did, where we cancel mass out as we keep everything in variable form. So on this one, go ahead and set up the free body diagram with the incline, and we know the acceleration now, and what you're going to do is work your way backwards to find the angle. So leave everything in variable form and set up the free body diagram, and once you do that, go ahead and see if you can determine the angle, and then if you need help, you can use the tutorial here to help the process. But go ahead and pause the clip and get as far as you can, and then hit play when you're ready. Okay, so here is the incline, normal force, force of gravity, surfer. We've got the coordinate axis set, force of gravity in y, force of gravity in axis set, and the normal forces cancel out perfectly by the force of gravity in y. Force of gravity in x, we have just the one force, and in variable form, this is mg is the hypotenuse. So we have mg times the sine of theta, and theta is what we're trying to find. We don't know what that is. And when we set up the forces, we can cancel mass from both sides. And so we're left with g sine theta equals the acceleration. We use the inverse sine to find our inverse sine of the value, and the angle of the ramp is 20.92 degrees.